Welcome students. Today we are going to discuss about solutions of some differential equations. Before we proceed, it's worth looking at this quote by George Euler. He was uh, one of the uh, big shots of his time. He was involved in numerical methods, but more importantly, combinatorics number theory. So let's try to look at the quote. It says, in order to solve this differential equation, you must look at it until a solution occurs to you. Surprisingly, in differential equation uh, business, a lot of times you can uh, basically, suggest the solution and then check if it is a solution or not instead of solving it. Okay, we'll come to those in some time. Before that, let's consider the following differential equation. We have y prime equals to ay minus b, where a and b are some constants and a is not zero. And we want to solve this differential equation. So let's just rewrite this differential equation in another format. So y prime here, the derivative is with respect to t. So we have dy by dt equals to ay minus b. Right? And with some rearrangement, you can take a common, you get y minus b by a. And if y is not equal to b by a, then you get what? You get dy by dt divided by y minus b by a equals to a. Okay. So you want to solve this differential equation. Now note that if you use the chain rule, or rather reverse of chain rule, you can see that on the left hand side you can write it as d by dt of ln of absolute value of y minus b by a equals to, right, because derivative of ln is 1 over that thing, right? So it will be 1 over y minus b by a multiplied by what? Multiplied by derivative of this, which is dy by dt, right? The sort of implicit differentiation happening there. So if you look at this expression using integrating on both sides or looking at the antiderivative, you can see that this is going to be ln of absolute value of y minus b by a equals to at plus a constant c, right? So whenever you're integrating, the constant c should come into the picture, right? This is very important, right? You cannot leave this out. Okay, so c is constant of integration. Now you can simplify this because solving this differential equation means solving for y. So we have y minus b by a absolute value is equal to e to the power a t plus c. This would mean y minus b by a is going to be plus or minus e to the power at plus c, which is plus or minus e to the power at times e to the power c. And I can call this, combine this as the constant, so we get what? Let's call this as a, another constant, e to the power a. So what do you get? You get, in the end, you get y equals to y of t equals to a e to the power at And this minus b by a goes on the other side, becomes plus b by a, where a is a constant. A is an arbitrary constant, non-zero constant. And the value of a is determined by what? By the initial value, right? So now let's consider a few scenarios. What if a was 0? If your a is 0, it's a constant. If your a is 0, then yt is what? Yt equals to b by a. Yeah, which is a constant solution. Yeah. However, this cannot happen because a is e to the power c and n exponential functions are never 0. Okay. So you saw this by inspection that you could use chain rule to solve this differential equation. So this is your solution to the differential equation here. However, we could have used, suppose you're not able to see that, we can use substitution to find this differential equation. So let's do that. So we'll use, so second method to solve the same equation. Second method, use substitution. So for this, let's take, so we have dy by dt equals to ay minus b. Let's call this as u. Okay. So if you take this as u, so let this be u, this would imply what? This would imply, take derivative on both sides, so you get du by dy equals to a, right? So du by dy is a, or du equals to what? We get du by a equals to dy. Now, coming back to this one, if I write it, I can write as dy by ay minus b equals to dt, right? And I'm integrating on both sides. Now on the left-hand side, I make this substitution. So this implies integral on the other side is going to be, so dy will turn into what? Dy will turn into du by a from here. So du by a, and the bottom turns into ay minus b turns into u. And this is same as 1 by a ln of absolute value of u equals to integral on the other side t plus some constant c. You'll say, why don't we add constant on both sides? You can add constant on both sides, and then you can move that around, right? So then you have c1 plus c2, and then you can move that constant on this side, right? So so we get this. Now we'll put back, multiply this. So we get ln of absolute value of u is e to the power, sorry, my bad, multiplying by a, both sides, so at plus ac, or this gives us, what does this gives us? Absolute value of u equals to e to the power at plus AC, or it gives me u equals to plus or minus e to the power at plus AC. And I can again do the same thing. I will call this as, this implies u equals to a e to the power at, where my a is equal to e to the power AC with a plus or minus sign. I'm going to replace that. Now you'll say, how can you replace both plus or minus sign? The idea is that at one point it will only be either positive or negative. Okay. So you get u equals to, so now let's put back what my u was. So my u was ay minus b. So I have ay, let's just change the pen color. So we have ay minus b equals to a e to the power at. And then this implies y equals to, bring this on the other side. So a e to the power at divided by plus b divided by a on both sides. And then I can absorb this and call a new constant, right? So the idea is, because a is an arbitrary constant, I can call it as a new constant. So let me call this as c e to the power at plus b by. So this is your solution. This is equal to y. And by earlier method, also by investigation, you found out. So don't worry about a and c because they are arbitrary constants. Okay, so this is the solution. This is how you would solve the differential equation of this kind. Now note that, so we have found out this is the differential equation where c is an arbitrary constant. Note that since c is arbitrary, there are infinitely many solutions to the differential equation, right? So such a solution is called the general solution. Yeah, so this solution is called general solution. Now, typically a general solution of a differential equation, the first derivative involving only the first derivative will have one arbitrary constant. Similarly, if it is a degree n differential equation, that means the highest derivative is of order n, then we'll have n arbitrary constants. Yeah, this is similar to the integration of n times. Now, those of you who did linear algebra, notice that differential equation can be thought of as, so let's say d by dt. Differential equation can be thought of as an operator from the set of functions. So can be vectors of vector space of functions to functions. And when you're looking at dy by dt equals to 0, you're looking at the null space of it. And if you take a linear operator and if you look at the kernel of it, you can make sense of what will be the dimension of the kernel or the null space. Okay, so it loosely corresponds to that. If you have d by dt, the dimension of the solution space is 1. So you have only one constant. You need only one constant to represent all the elements of that space. All right, this is outside our discussion. But anyway, if you're interested, you should look at it from that perspective and talk to me in my office hours. All right, so let's move ahead now. So generally, you want to pick up one solution which fits your physical problem or the problem you're trying to solve. So such problems are called initial value problem. Recall what was the initial value problem. So you have y equals to ay minus b. Of course, this, if you look at this, we have already solved this. The solution looks like that. Question is, what is the constant? So if you're given the initial condition, that means value of your y at some point, then you can solve this problem. Okay. So let's try to do that. So initial value problem is basically you're given the differential equation. If it is of order 1, then you're given some value of the function at some point. Yeah, so y of 0 is y0. Y0 is some fixed number, okay, where y0 is called the initial condition. Yeah, note that the initial condition need not be just given at 0. It can be given at any point. All right. So let's try to solve this differential equation with the initial condition. So we have already solved earlier y prime equals to ay minus b and y of 0 equals to y0. So this gives me what? So this is what is called as initial value problem, short for I. So the short is IVP, a differential equation. So this is basically a differential equation plus an initial condition. Now we have already solved the DE, the differential equation. So what did we get when we solved the differential equation? We got yt equals to c e to the power at plus b by a, where c is a constant of, c is constant, arbitrary constant. However, now that we have given y of 0 is y naught, let's try to see what this c could be. So y of 0, that means I put t equals to 0, I get e to the power 0 plus b by a, which is going to be c plus b by a. But on the other hand, I'm given y0 equals to y naught, the value of the function at 0. So if you compare these two, you will see that c is simply y naught minus b by a, right? So this basically gives you, this implies your yt, the solution to this initial value problem is going to be, instead of c, I will have y naught minus b by a times e to the power at plus b by a. Yeah, so this is not an arbitrary constant. All right, now this is fixed. You know what is y0, it is already given to you. You have b by a, so this so this is a solution to your differential equation. All right, now let's revisit the problem of the falling object as an initial value problem with initial velocity v of 0 is 0. So if you recall the IVP, the initial value problem, VP was given by, this was given by V prime equals to 10 minus 2V with extra, now you're given the initial condition, which is V of 0 equals to 0. Now, if you compare with this guy, the general solution is going to be, what is the general solution? Let's see. So here, if you compare with this differential equation, your A is minus 2, A is minus 2, your B is, what is your B? Your B is minus 10, right? So A is minus 2, B is minus 10. Okay, so the solution is going to be, and of course, Y0 is, or V0 rather, because the variable is V0 is 0. So if you look at and substitute in this equation, you will get V of t equals to Y0 minus B by A. So minus of B, which is what? B is minus 10 by A, which is minus 2 times e to the power at, which is minus 2t, plus b by a, sorry, so plus b by a is going to be plus minus 10 divided by minus 2. And if I write it, this is going to be minus 10 by minus 2 is 5, so minus 5. So minus 5. Then what do I get? Minus 5 e to the minus 2t plus 5. Or I can take 5 common. So we have 5, 1 minus, I'm rearranging it slightly, 2t. So this is your solution to IBP. So this is a solution to IBP. All right, so this solves this problem. Now, okay, so let's proceed further. If the question, if the object is dropped from a height of 100 meter, how long will it take until it hits the ground? So we are still continuing with the same problem, right? Now we are given the velocity and we are asked, given this velocity, if the height, if you're dropping it from 100 meter height, how long will it take to hit the ground? So again, let's formulate this IVP. So formulation, so formulate this IVP. So what do we get? For what? For the drop, let's call that as X variable, X of t. So again, let's basically, if you want, we can draw a picture of this. So the idea is you have, let's say this is ground. So this is your ground. This height is 100 meter and your object is falling down with velocity v, right? So now we have, so we can now do this problem. So we have, you're given the velocity, which is x prime of t. So this is your x is 5, 1 minus e to the power minus 2t. Yeah, you may say, well, the height x is decreasing, right? So you can change your the outlook for this. What way can we look at the outlook? So this corresponds to, so let's this x be the distance from here to here. Let this be x at time t. So you will have x of 0 is 0, right? And you're seeing question is what is, so you have basically this whole thing is x of, so you are interested in for what t, for what t gives x of t equals to 100, right? Because you're starting from here, this is your height 0. Let me just write it down here. Height equals to 0, and here the height equals to 100. Okay. So let me make a space here so that difference between them is clear here. So we want to solve this differential equation now. So we get dx by dt again equals to 5, 1 minus e to the power minus 2t. So what do we get? We get dx. This is separable differential equation. Minus 2t dt. Integrate on both sides. So you get x equals to 5t minus 5 e to the power minus 2t. Integration is e to the power minus 2t divided by minus 2. And that minus 2 will make this as plus. And then plus a constant c. All right, this constant c is very important. All right, so the idea is because there are many solutions to this differential equation, right? Now, but you are given the following: x of 0 equals to 0. So in this case, we get what? We get um, x of 0 equals to 0. So I'll put 0 on put. So let t equals to 0. In that case, on one side, we'll get x of 0 equals to, on one side, you get 0. On the other side, you get what? You get 5 by 2 plus c. So therefore, c equals to minus 5 by 2. Then you put it back in your differential equation. This gives me what? This gives me x of t equals to 5t plus 5 by 2 e to the power minus 2t minus 5 by 2. And if you look further, you will see, so this is your solution. However, you're looking for what? You want t equals to capital T such that x of t equals to 100. So put this information in your function. So you get 100 equals to 5t plus 5 by 2 e to the power minus 2t minus 5 by 2. Now bring this guy on the other side, or this one on this side. So you'll get 5t plus 5 by 2 e to the power minus 2t. 100 minus 5 by 2 is going to be 200 minus 5, 200 by 2 minus 5 by 2, which is going to be 205 by 2 equals to 0. So this is what your t is. Now you can't solve this directly, so use numerical methods. Now, do we know any numerical methods? Of course you do. You know about Newton's method in your Calc 1. Newton's method was devised to find the solution or zero of an equation, right? So you can use that. However, we can see that this is going to be roughly 20.5 and things are measured in seconds. So, okay. So this is a solution. You need numerical method because you can't solve this algebraically, right? This equation cannot be solved algebraically, right? Yeah. At least I don't know how to solve this algebraically at the moment, right? So you can use numerical method and this will be the solution. All right, so let's recap what we have done. We have solved a very particular differential equation today, and we applied it to the problem of the previous class, which was a velocity problem, and we got to here. So thank you for your attention. See you later.